Hi everyone, today we're gonna go through practical big O examples. What this means is that I'm gonna show you some snippets of code and we're actually gonna calculate the big O time complexity. This is a fundamental skill you need to have in order to pass any kind of technical interview. In fact, after you finish writing your code, during an interview, the interviewer is gonna ask you at the end, "Oh, could you please tell me the time complexity?" And it's important that you know how to calculate the time complexity of what you have actually written. I highly suggest you watch my previous video. It's a short 10-minute video that goes through the theory behind the big O notation, and it contains everything you need to know for your technical interview. It's not a prerequisite, but I highly suggest you watch it before watching this video. Before looking into the actual example, I just want to briefly recap what big O is. It is the analysis of an algorithm's performance as input n grows. With big O, in an interview, we measure the worst case. You might be wondering, why do we measure the worst case? Let's look at these simple examples. So in the first one, we've got an input array with 10 elements. And we are searching for number 2. We have a for loop that is going to go through all the elements of the input array. And when we find the target number, we are going to print it and then stop. In the first example, number 2 appears after 3 iterations. In the second one, our target 9 is at the end of the array, which means that we are gonna go through all the elements of the input array, where n is the number of input elements. It means that we had to do n operations, and that's the worst case. So this is why we measure the worst case. It's because for different inputs, we could have different behaviors, and we always want to look at the worst behavior possible. In the last example, we have a number 15, which never appears in the input array, but we're still gonna go through all the elements of the input array. The time complexities for all 3 of these is big O of n, because in the worst case, we will have to iterate through n elements, and n is the number of elements in the input array. This is just a quick recap of the most common time complexities you're gonna come across during interviews. On the left, we've got the best one, which is constant time. And on the right hand side, we've got the factorial time complexity, which is one of the worst ones you can get, and we should probably avoid it during an interview, but also in real life. When analyzing an algorithm, you need to be aware of the fact that the constants get dropped. So in this snippet of code, we have a single for loop with 2 if conditions inside, and here we've got 2 for loops. So what might happen in this case is that when a person is gonna see 2 for loops, they're gonna say, "Oh, this is gonna take big O of 2n time." They're gonna add these 2 just to be more precise, but this is not being more precise. This is not needed. In computer science, when you're actually analyzing the time complexity of an algorithm, we just care about how the algorithm behaves as the input increases. In this case, we don't care about the constants, so this is gonna get dropped, and this is simply going to become big O of n. If we look at this example here, we have a for loop with 2 instructions, and a for loop which is going through each element of the array is gonna take big O of n time. In this case, n is the number of elements in this array. And then we've got 2 ifs. Each of these is gonna take constant time. At each iteration, we do 2 operations. So this could be written as big O of n times 1 plus 1, so times 2. So again, as we see, this 2 is a constant. So we just remove that, and we have big O of n time. So as we saw, we have dropped the constants. We don't really care if you've got 2 for loops. Here we have 1 for loop with 2 operations in it. To actually see which one is more performant, we would need to go into the actual low level code, but that would be a real mess. So we just drop constants and we don't look at that level of detail. Another thing you need to know is that we drop non-dominant terms. So what this means is that when you've got a time complexity like this, so this could be represented by 2 for loops which are nested, plus another for loop outside. You could come up with a time complexity like this, n squared plus n. In this case, what dropping non-dominant term means is that we get rid of the smallest of these two terms. So in this case, n takes less time than n squared. We just care about this portion of the time complexity. So we're gonna say that the time complexity of our algorithm is n squared, because as I said, in computer science, when analyzing an algorithm, we just care about the worst case. Okay, let's look at this second example. We have an n plus log n. We know that log n takes less time than big O of n, so we're gonna get rid of this term, and the most dominant term is just big O of n. So over here, as we can see, we've got some constants, so let's eliminate those first. So let's eliminate this 5, this one here. Now we've got n to the power of 100, and then we've got 2 to the power of n. We know that this one is bigger than n to the power of 100, so we're gonna get rid of this term here, and this is gonna become big O of 2 to the power of n. And last one, so some people might say, oh, this is just gonna be big O of b to the power of 2, but that's wrong. And this is because we don't know what's the relation between b and a. This could be like a huge number, this could be a small one. We don't know what's the relation between these two. So this time complexity is gonna stay the same. You need to be able to identify when to add or multiply a time complexity. So let's say you have an algorithm that has 2 steps. How do you know when to multiply and when to add the time complexities? So let's take these 2 examples, example 1 and example 2. So on the left, as the comment suggests, we add the time complexities. In this case, we've got 2 arrays, array A and array B, and the time complexity here is A plus B. What happens here is that we do A chunks of work and then we do B chunks of work. So when you have this kind of pattern, do this bit, and then when all of this has finished, do this other bit. We add the time complexities. This is big O of A and this is big O of B. When we add them, we get big O of A plus B. In example 2, instead, we've got the following. We do B chunks of work for each element in the array A. So when you have this kind of pattern, do this for each element of this other array. We want to multiply. So in this case, we've got array A and array B, and we're going to multiply them. This is not to confuse. Sometimes people might just see a nested for loop and say, oh, this is n squared, or they might say, oh, this is a squared. You need to keep into account that these two are different arrays. If this one was array A, this would have been fine, but this is a different array. It might have a different number of elements, so we want to always differentiate. So this is gonna be A times B. So before carrying on, let's look at these examples. What we want to do is we want to find expressions which are equivalent to big O of n. So let's start with the first example. We know that P is less than half of n. So in this case, we know that P is smaller than n, so we can drop the non-dominant term, which is p in this case, and this is gonna be equals to big O of n. Second one, we have big O of 2 times n. As we learned earlier, we drop constants, so this becomes big O of n. So over here, we've got n plus log n. So we know that we drop non-dominant terms. In this case, we drop this one, and this becomes big O of n as well. So this is equivalent to the time complexity we are looking for. Lastly, big O of n plus m. So in this case, we don't know what's the relation between n and m. So we're gonna keep both of these, and this is not equivalent to big O of n. I hope this part was clear. If you have any comments or questions, just leave them in the comment box below. Okay, let's now start by looking at how to identify when an algorithm runs in constant time. So what constant time means is that no matter how big the input, the algorithm's runtime is gonna remain constant. So let's look at this example 1. Someone might confuse this with big O of n runtime complexity, but that would be wrong, because if you look closely here, we can see that this for loop is always gonna run maximum 100,000 times, no matter how big the array or anything. So this is constant. So that's why this is big O of 1 runtime complexity. So let's look at another example. Here we've got an if statement. What you can notice is there is no loop. We just have a comparison. It's one instruction. 2 items are being compared. And no matter how big A or B, this comparison, which is the main operation, is going to take the same amount of time. And exactly the same for this other statement here. This system print ln is going to always take the same amount of time. It doesn't matter how big the input. So this is going to take constant time as well. Let's look at our third example now. When you've got an array, and let's say you're accessing a specific index of this array, in this case index 3, this is gonna print number 3 because this is the third index. Because you're accessing the index directly, this is gonna take big O of 1 runtime. This is to not be confused with when you are iterating over an array. So when you're iterating over an array, it's going to be big O of n. But when you're accessing an element directly using the index, that's going to take constant time. Let's look at our last example. So in this example, we've got a hash map with some values in it. And then we've got a retrieve operation. So we're going to get the value with key 2. So the way hash map is implemented is it uses a hash function. This operation, this hashing operation, happens in constant time. So this statement here is going to take big O of 1 time. And same when you put something in a hash map, there is going to be a hash function. We're going to calculate the hash function and then insert it. So the same here, this is going to take big O of 1 time. No matter how big the input, the hashing function is going to take constant time. Let's now look into logarithmic time complexity. So in this case, performance grows logarithmically with the input size. And this is a desirable time complexity to have when writing an algorithm. If you have solved LeetCode questions, you know that this usually appears when you are dealing with binary search. So we got an example here. We have an input array, and what happens with binary search is that we're going to have a middle. If this middle is the same as the value we are looking for, we're going to stop. Otherwise, we're going to check. If the value we're looking for is smaller than the middle, we're going to eliminate all the right part of the input and we're just going to focus on the left hand side. Then again here, we're going to look into the middle of this new restricted input array and check if this middle is smaller or bigger. And according to that, we're gonna get rid of half of the search space. And as you can see, each time we do this operation, we halve our search space. So let's say we start with an array of input size n. After a single step, we're going to be down to n over 2 elements. After another step, we're going to be down to n over 4. We are going to stop when we either find the value or when we're down to just one element. So the total runtime is then a matter of how many steps we can take until n becomes 1. We have another example here. As you can see, what makes this run in log n time is this incrementer for I. So every time at each cycle, I is divided by 2. And that is what makes this logarithmic time. Linear runtime complexity, it's another one that you're gonna face quite often when solving LeetCode questions. In this case, the performance is directly proportional to the input size. So if the input size doubles, the runtime is also going to double. And there is a pattern to identify this kind of time complexity. So usually this appears when you have, let's say, an array or like a hash map. When you have a piece of code that is iterating through each element of your array or your hash map, that's an indication that that's probably gonna be a linear time algorithm. But make sure you don't confuse it with a quadratic time complexity, which is when you have, for example, 2 nested for loops. You have to pay attention to that. So linear time happens when given an input of n elements, you are iterating through all of them in the worst case. Let's say you were looking for a number here and you had a for loop that iterates through each element of this input array until you find this element s. So you don't know where s could be. It could be either at the beginning or at the end. So that's why this is linear time complexity, because just let me remind you, we are looking for the worst possible case. Let's now look into another time complexity that you will encounter when you have to deal with some kind of sorting. So this complexity is commonly found in efficient sorting algorithms like merge sort and quick sort. So let's look at this example. So let's say you're given this piece of code and they ask you to find the time complexity. So let's break it down. So we have an array and then we have this array.sort call. So this is going to use the integrated sort function by Python. And Python uses something called timsort, which is a combination of merge sort and insertion sort. And the time complexity of this operation is big O of n log n. Next, we've got a for loop that is printing each element in the input array. So this is going to be big O of n. So as we remember, now we need to sum these two together. But if you remember, we dropped the non-dominant term. So in this case is n. So the time complexity of this whole piece of code is big O of n log n. In this example here, instead, we're using the heapify function that is embedded into Python. So we have an input list and we want to transform it into a heap. So this heapify function takes big O of n log n time. So the whole time complexity of this algorithm is this one. As you saw, you have to be good at the programming language you use to tackle your interviews, and you need to know what the time complexity is of these built-in functions you are using, because as you saw, for example, here, if I didn't know that this sort took n log n time and I just said that this is going to take big O of n time, that would have been wrong. So you just have to be a bit careful. Okay, let's look at quadratic time complexity. So this is something that you're going to encounter during your interviews. And in my experience, this is usually seen with matrix problems. But let's look at this example first. In this case, we've got an input array. We have 2 for loops. The first for loop goes through each element of this array, and the same for the second loop as well. So in both cases, we have the same array which has n elements. For each element of this array we deal with, we're going to go through also all the other elements of this input array. So this pattern here, 2 nested for loops, suggests that the time complexity of this piece of code is big O of n squared. Again, let's look at this example to a similar case. We have an input array and we can see that we've got 2 nested for loops. Both these for loops are iterating through this input array, but one is nested into the other. This again suggests that this is going to be quadratic time complexity. The difference we see here is that this j starts at I plus 1 and this one starts at 0. This doesn't make any difference. As we said, we drop non-dominant terms and we drop constants, so this comes under one of those cases. We have an example here. So some people, when looking at this code, might say, oh, this is n squared because there are 2 nested for loops. If you look closely, one is array A, one is array B. The time complexity of this piece of code is not n squared, but it's actually big O of A times B. And this is because we don't know what's the relation between A and B. They are 2 different arrays, and for each element in A we do B work. So as we saw at the beginning, in this case we multiply the time complexities and this is the result we get. Let's see exponential time complexity. So in this case, the algorithm's performance is going to grow exponentially as the input grows. So this is highly inefficient and we should try to avoid having an algorithm with this time complexity, and especially if we have large inputs. Let's look at this example here. We're calculating the Fibonacci sequence up until a number n. So in this case, we can see that at each iteration we have 2 branches and we go as deep as n. So the runtime complexity for this algorithm is big O of 2 to the power of n. So there is this rule that you can generally use to identify the time complexity. This kind of time complexity usually appears when you have this kind of recursive calls. I think it would really help if you looked at more examples online or you did more LeetCode questions. But yeah, this is the general rule of thumb. I also want to highlight that these examples I'm showing you, they are from Cracking the Coding interview book. If you want more detail, I suggest you get that book. Lastly, let's look at factorial time complexity. So this is extremely inefficient, and we usually should just use this for small inputs and we should try to avoid it at all costs. This is not really common when solving LeetCode questions, but I still wanted to show you an example. And if you don't know what factorial number is, let me just give you an example. So let's say you want factorial 2. The result is going to be 1 times 2. Or let's say you had factorial 3. This would be equal to 1 times 2 times 3. Which is equal to 6, this is equal to 2, and so on. Let's say you had factorial 4, same as factorial 3, but you just multiply by 4 as well. So as you can see, between factorial 2, factorial 3, and factorial 4, there is a big jump. We go from 2 to 6 and to 24. By just looking at this, you can see how inefficient this algorithm is gonna be. So just to conclude this, remember these relationships between the time complexities. This is the best one, this is the worst one. Your aim is to try and stay on this side of this statement. You should try to avoid using these. You should try to write an algorithm that runs in any of these runtime, both when solving a LeetCode question but also in real life. It might not be easy, but the more you're gonna practice, the better you're gonna get. And I hope this was useful. If you have any questions or anything you want to raise, just leave a comment below. If you found this video useful, please like and subscribe. Also check out my YouTube channel. You're gonna find many more LeetCode questions and other videos that I hope you're gonna find useful to prepare for your technical interviews. Thank you.